All right, the next topic we are going to look at is the linear elasticity of solids, and I assume that you are already familiar with Hooke's law, which says that the stress is proportional to the strain. So in its simplest form, Hooke's law says that the stress on a solid is proportional to the strain that it displays as a result of this stress, where stress is defined as force per unit area in some suitable circumstance, and the strain is defined as the deformation of this object relative to its original disposition. Now this law as it stands is extremely vague, but we need to make it very quantitative, which we will do in a minute. But I must say right away that this is a very restrictive law, because it essentially says that when you deform an object, a solid to be specific, the response of this object, the strain, has three properties. One, the response is linear in the sense that it is proportional to the stimulus that you apply. Two, that it is fully reversible. In other words, you remove the stress and the object goes back to its original form completely, totally reversible. And three, that the response is time independent. In the sense that the response is instantaneous. You apply the stress and immediately there is a deformation, and you remove the stress and immediately it goes back to its original disposition or configuration. None of these is true in practice really, except under very special circumstances. First, for linearity you need to have very small stresses in some sense. For reversibility you have to make sure again that there is no permanent deformation of the material. If you take a paper clip and you bend it, you remove the bending force, it remains bent, and that is a permanent deformation, and that does not fall under Hooke's law at all. And thirdly, that it is time independent in the sense that if I apply a stress to an object, there may be an instantaneous or practically instantaneous response, but if you wait long enough, this response will slowly saturate to some new value or go on forever. For instance, if I pull an object with a sufficiently high load, you can see that if it is a thin rod of metal, this metal, if the load is high enough, will stretch and stretch and stretch, and it will form a narrower and narrower neck, and finally it will break. So this is clearly time dependent. Now none of these things comes under the purview of Hooke's law. So this is essentially a linear law for small deformations under very special circumstances. Then you can plot, and we are going to say what the stress and strain are in detail. The conventional symbol is epsilon for the strain and sigma for the stress here. And the statement is that typically if you apply small strains, the stress is proportional to it, so it is linear, and then after a while it leaves the elastic region, there is what is called a yield drop, and then it goes and for a long time it flows, and then it takes off, flows much more rapidly, and finally it breaks at that point. By the time you reach this, the strain is like 20 or 30% or more, depends on the material. Now what we are talking about, the Hooke's region, the region of applicability of Hooke's law is just here. This is where Hooke's law will apply, this region. But now we have to ask, what do I mean by this stress? What kind of stress is there? Are there different kinds of stress, different kinds of strain? And the answer is yes, and this is what we are going to talk about. The simplest one in the way of looking at this is as follows. Imagine a unit cube of some material. So these are the coordinate axes. Let us put coordinate axes here. That is the origin of coordinates. This is the x direction, the y direction, and the z direction. I will find it convenient to call this the one direction, this the two direction, and this the three direction. It is much more convenient to label them as 1, 2, 3, and then we are very clear as to what we mean. Now imagine this unit cube of this material, and imagine holding three of the faces fixed. So this face, the side face, the back face, and the bottom face are stuck to the coordinate axis, they are fixed, and whatever stress I apply will be applicable on the other 3 faces here. Then the following kinds of stresses can be applied. I could go to the center of this and apply, solder a hook onto it and pull it upwards, or pull this downwards, or do both along the 3 axes here, and I call that uniaxial tension. So this is uniaxial tension, and the stress is uniaxial tension, and this can be measured by the load per unit area, the force per unit area on this unit cube. I can similarly push it inwards, and that's uniaxial compression. All that will happen is that the sign of this stress will change. So if it's plus, it's pulling, and if it's minus, it's pushing inwards. And of course, you immediately begin to see intuitively that materials can have different responses for pushing and pulling. There are materials like glass which can stand a lot of pushing, but it would not stand any pulling. It will become brittle and break. So there is some inhomogeneity, but we won't worry about that right now. We are talking about, say, metals, typical metals, where this asymmetry is not present. So you could have a uniaxial tension along the 3 direction, or similarly along these directions, or for that matter you can come out of the board and go in this fashion. So along the 1, 2 and 3 directions you can have uniaxial tension, or you can have a combination of 2, biaxial if it's along 2 axes, triaxial if it's got all the 3 axes, and so on. And the stresses corresponding to it I am going to call sigma 1 1, sigma 2 2 and sigma 3 3. In other words, they are applied on faces normal to the first index and in the direction of the second index. So this here, this stress would be sigma 3 3, because it's in a face normal to the z axis, parallel to the xy plane, and it's along the z3 direction. So it's sigma 3 3. So I hope that notation is clear. These are all tensions, uniaxial, biaxial, triaxial tensions, or compressions. Similarly, one can now do the following. One can hold this face fixed and shear it in this direction, or shear it in this direction, or shear it in the third direction outwards. So again, I'm going to denote by sigma subscript I and j. This is going to be normal to this direction, and it's along this direction. Then what do the various shears look like? Well, we got to draw another figure for that, so let's do that. This comes out, there's a unit cube here, this fashion. And now what's sigma 1 2 going to look like? For instance, it's got to be normal to the one direction, so it's on the front face, and it must go along the 2 directions. So I take this front face and shear it like this. So I keep everything fixed and shear the front of the cube in this direction. That's going to be sigma 1 2. Remember, there's a 1 direction, 2 direction and 3 directions. What about sigma 2 3? It's got to be normal to this direction. So it's on this face because the back face is fixed, and along the 3 directions, so it moves up like this, 2 3. And sigma 3 1 will be on the top face, normal to the 3 direction, parallel to the xy plane, and it should be 3 1, and therefore it should come out in this fashion. And this is sigma 3 1. These are shears. Sigma ij, I not equal to j, is a shear. And there are 3 other shears. There is sigma 2 3 and 3 2, and 1 2 and 2 1, and the third one which is 3 1 and 1 3. It's very convenient therefore to write this whole thing as a matrix. So write this as sigma 1 1, sigma 1 2, sigma 1 3. So you really have 9 different kinds of stress that you can apply to a unit cube of material. Okay. And if the system is linear, if the response is linear, you're going to have 9 different kinds of strain as well corresponding to these. Some would be shear strains, some would be tensile strain or compressive strains, etc., exactly as in the tension case. But if the material is merely linear, then the strain too in general can be written as epsilon 1 1, epsilon 1 2, epsilon 1 3. If the material is linear, all it says is, Hooke's law says is, any given strain is linear in the stresses, proportional to the stresses. But there are a whole lot of stresses and you can apply all of them simultaneously. So it immediately says that each component of this strain, each of these 9 components is a linear combination of all these 9 out here with some coefficients. So how many coefficients of or moduli of elasticity do you have? Whatever you call this stress is equal to elastic modulus multiplied by strain. And how many such coefficients of elastic modulus can one find? Well, you have 9 strains and each of them is a combination of 9 stresses. So in general there are 81 elastic moduli. But now there is a huge amount of reduction as follows. First of all, one can show that for thermodynamic stability, for stability of this system, it turns out that sigma ij must be equal to sigma ji, and similarly epsilon ij must be equal to epsilon ji. This means you don't have 9 independent quantities. You have 1, 2, 3, 4, 5, 6, and these are the same as those. So you have only 6 independent stresses possible, 3 strain, 3 tensions or compressions, and 3 shears, and you have 6 strain components. And therefore, when you write each of these as a linear combination of all the others, you don't have 81 coefficients, but you have only 36 coefficients, which is already a big reduction. But there are further symmetries in the problem, and it turns out that in almost all cases that we know of, that we can conceive, the number is reduced enormously, much more. And in fact, in the case of media which are isotropic, which is the only thing we are going to look at, same properties in all directions, not like a crystal which is anisotropic, or not like a composite material which sometimes has different properties in different directions. All of you know that when you take a ruler and you bend it in one direction, it bends easily, it's very flexible, but if you bend it another direction, it cracks. So these are composite materials which are non-isotropic, but for isotropic media, it turns out you have only 2 independent elastic moduli, just 2. So for such media, and those are the ones we are going to look at, you have only 2 independent elastic constants, and let me write this down. Isotropic medium material, only 2 independent elastic moduli. And you're familiar already with what these are, and let's write it down. Under tension, you know that sigma 1 1 equal to the Young's modulus times epsilon 1 1, and this is called the Young's modulus. And therefore, since it's isotropic, sigma 2 2 is the same y times epsilon 2 2, sigma 3 3 equal to the same y times epsilon 3 3. Okay. So much for 1 elastic modulus. Now we need to put in some numbers. How big are these fellows? Well, the strain is dimensionless, physically dimensionless, because the strain, if you pull it for instance and the original length is L and it's pulled by a delta L, the strain is defined as delta L over L, which is dimensionless, no physical dimensions. Stress is force per unit area, so this is m L T to the minus 2 over L squared. That's the dimensions of stress, and it's measured in newtons per meter squared. And typically for most metals that we know of, this Young's modulus is of the order of 10 to the 11 newtons per meter squared. Yeah. So that's the order of magnitude we are talking about. If you look at softer materials like bone or something like that, it will be an order of magnitude smaller and so on. So this is typically a figure here. So stresses or the Young's have the same dimensions as the elastic moduli, and they are typically of the order of 10 to the 11 newtons per meter squared. Now one can compress the system in all directions, and then you apply what's called hydrostatic pressure, and the system will undergo a change in volume, and that is measured by the bulk modulus. So the bulk modulus, as we normally define it, bulk modulus, this is equal to the stress, which is a pressure, hydrostatic pressure, this would mean that you apply sigma 11, sigma 22, sigma 33 and push them all in all directions, divided by the strain, which is the change in volume over the original volume. So this is volumetric strain. Here. K, and the symbol generally used for it is K. Okay. And finally, there is a shear modulus which says shear modulus G. Oh yes, I should also say how it's related to the stress tensor here. This here is nothing but sigma 11 plus sigma 22 plus sigma 33. It's the trace of this matrix, and that's what you normally call the pressure. The hydrostatic pressure is defined as the trace of this matrix, which you write down for all the strains, no shears involved, and that's divided by the volumetric strain, which is 11 plus epsilon 22 plus epsilon 33. That's reasonable too. You already know this because you see, if you have a cube or a rectangular parallelepiped of size x, y, z, so let's suppose you have an object which looks like with the 3 dimensions being this is x, this is y and z, then as you know the volume of this object is x, y, z, and then it's immediately clear that delta v, if I differentiate it, is delta x multiplied by yz plus delta y multiplied by zx plus delta z multiplied by xy, and therefore if you divide it by v, which is x, y, z, you end up with delta x over x plus delta y over y plus delta z over z. But this is precisely what we've called epsilon 11 plus epsilon 22 plus epsilon 33. Strain in the x direction, y direction and z direction. Here. So this is our definition of the bulk modulus here. And the shear modulus is again the shear strain stress divided by the shear strain. And as I said, for an isotropic medium, there's just one shear modulus, one bulk modulus and one Young's modulus, and the 3 are related. So the relation between them goes like this. For an isotropic medium, 3 over y equal to 1 over g plus 1 over 3k. That's not very hard to prove. In fact, we'll partially prove it in a very short while. But there's a relation between the three elastic moduli, so you really have only two independent elastic moduli, any two that you choose. By the way, this also tells you that, gives you a hint that all the elastic moduli are of the same order of magnitude. So for a material which has got a Young's modulus of 10 to the 11 newtons per meter squared, the bulk modulus will also be of the same order of magnitude, as will the shear modulus, okay, give or take some factors. So this is a crucial relationship proved fairly easily, but more important than these elastic moduli, I said there are two independent ones, and the question is which ones do you choose? Actually, these are not the best ones to choose. The ones to choose are perhaps this Young's modulus and one more modulus called the Poisson ratio. And Poisson's ratio is as follows. It says if I take an object like a rod, for example, with a rectangular cross section, let's draw it properly. And pull it in this direction by applying a load, then you know that the lateral directions go inwards, they get compressed inside, okay. And if this is the 3 direction, this is sigma 3 3, the stress applied in the 3 direction, then Poisson's ratio nu is defined as the lateral strain divided by the longitudinal strain. The longitudinal strain, of course, is epsilon 3 3, and the lateral strain has a minus sign because it's going inwards, epsilon 1 1, or in this case of isotropic medium, 2 2 over epsilon 3 3. So that's what Poisson's ratio is. But there's a limit on this here, a very interesting limit on this ratio. It turns out that for most materials that you're familiar with, like metals, steel, copper, etc., Poisson's ratio is somewhere between 1/4 and 1/3, so between 0.25 and 0.3 or so in general. But there are strong bounds on it which you can get from this relation here, because all you have to notice is that delta V over V, and let's say we have uniaxial tension pulling outwards. In this case, this quantity is equal to when you pull outwards, we can ask what's the change in the total volume. Well, delta Z over Z, this guy here, is going to be epsilon 3 3, okay. But this is going to be the ratio epsilon 1 1 is minus nu times epsilon 3 3. So this is minus nu epsilon 3 3, this is minus nu epsilon 3 3, this is epsilon 3 3. So this thing becomes 1 minus 2 nu times epsilon 3 3. But that is equal to 1 minus 2 nu times sigma 3 3 is equal to sigma 3 3, the tension that you apply, divided by Young's modulus. Because y times epsilon 3 3 is sigma 3 3. Okay. Now when you apply an extension and a tension which pulls the system outwards, by stability you cannot have a decrease in volume. It violates Le Chatelier's principle. It violates stability. So this thing has to be greater than 0, which implies immediately that nu must be less than a half. You can't have a material with in simple linear elasticity with a Poisson ratio which exceeds a half. In practice you find it's of the order of 1/3, but this is a strong bound. For such materials you cannot have a Poisson ratio greater than half. And in fact there's a relation which tells you the following. We can prove, and you can prove just by extending this a little bit, that y can be written as 3k times 1 minus 2 nu. So there is a fundamental relation between Young's modulus, the Poisson ratio, and the bulk modulus. As I said, there are only 2 of these constants which are independent. You have 4 of them now. You have y, the Young's modulus, you have k, the bulk modulus, you have g, the shear modulus, and you have nu, the Poisson ratio. So there have to be relations between them, and stability dictates what these relations are. One of them is this, and similarly this can also be shown equal to twice g, and this is the shear modulus times 1 plus nu here. And the Young's modulus must again be positive, and that implies immediately, these 2 relations immediately imply that -1 is less than nu less than a half. So Poisson's ratio cannot lie be less than -1 and cannot be greater than plus half, and as I said, in most cases is of the order of 0.25 to 0.30, very roughly for these. Of course there are materials where this is not true, but they may not lie within the purview of linear elasticity. They may be composites, they may be complex materials, and so on. They may have very loose structure, be porous, for instance. You may ask why Poisson's ratio could ever become negative. It can, once you have a material that's sufficiently networked in very loose bonds. Here's an example. Here's a sheet of paper, and I crumple it up, and imagine for a moment this is a solid, and now watch what happens when I pull in this direction. You see, when I pull in this direction, in the transverse direction, it also goes up. So that's a crude way of seeing that when you have objects which are not simple looking, simple objects, which are not homogeneous, they are very heterogeneous, the structure is like a composite material, then you can have negative Poisson ratio. When you pull chicken mesh, for example, it will go in the other direction, or styrofoam. But then in most normal circumstances, Poisson's ratio is indeed between 0.25 and 0.3, and one can show a little bit more work that between -1 and 0 you have one class of materials, between 0 and 1/5 you have another class, and between 1/5 and a half would be the traditional class of simple materials for which linear elasticity theory holds in its present form. On the other hand, I should immediately say that this is only in the elastic region, and only in the case of instant response, completely reversible time independent response. And in real materials, when the stress becomes sufficiently large, you end up with the region of permanent deformation, and that arises due to very different mechanisms altogether than what elastic deformation arises due to. By the way, even elastic deformation is not instantaneous. Nothing can be instantaneous. It's very fast compared to the time scales you are interested in. If you take a thing like this and you clamp this end and you apply a load on this end that's applying uniaxial tension, the stress has to propagate from here to the rest of the medium, has to go all the way here, and it cannot do so faster than the speed of sound in the medium. And that might happen in milliseconds for normal laboratory conditions. So you think it's instantaneous response, but actually it is not instantaneous in the technical sense of the word, but for all practical purposes it is instantaneous. So the thing about elasticity that's worth emphasizing is that one should understand the region or regime in which linear elasticity is valid and all these nice properties are valid. But then given Hooke's law, one can go a great distance in understanding deformation behavior of materials in this region of applicability.